Well, hello DNA replication fans. Today I'm using ScreenChomp for our tutorial. So let's go ahead and begin. So what I've set up for you first is our standard replication bubble, where you can see we have an origin of replication here, right, written in orange. And the green denotes the RNA primers that need to sit down to begin replication. Right? Remember, DNA polymerases cannot start complementary base pairing to naked DNA. They must have an existing 3' OH from a nucleotide to begin replication. In this case, they'll use one of the ribonucleotides that the enzyme primase sets down. Those, again, are in green. And then in red, we can see the new strands that are complementary base paired by DNA polymerase, with their polarities listed so that you can see that, yes, they are all anti-parallel to the template strands, right? The template strands are in black, so I'm outlining one in purple, the other guy. So these were the two original strands of the DNA molecule. And as you can see, the red strand, or the red complementary base paired nucleotides, going towards the crotch, there's the crotch, right there. What would we call that? We would call that new strand the leading strand. Okay, that automatically makes the opposite strand on the same side of the origin the lagging strand, right? Or the strand that is moving towards the origin, which then makes this one the leading strand, and this guy up here the lagging strand. Okay, so let's zoom in on one side of this bubble just to get a better idea of what's going on once this part has happened. And look, there it is. So we're just going to look at the right side of the bubble, and so I've taken the liberty to draw some of this stuff in already. And again, I will label this guy is the leading strand, right, because he's moving right into the crotch, right, 3' end. And then this other strand will be the lagging strand. And you can make note that when we talk about the leading strand and the lagging strand, we're talking about the newly made strand, not the template. So we wouldn't want to label this template strand lagging. We want to label this new strand lagging and this new strand leading. Okay, so once we get to this point, what do we have to do? We want to get rid of the RNA primers. That was a question that was asked in class a couple different times. Well, what do we do? Right? Your chromosomes do not have ribonucleotides in them. We need to get rid of all the green stuff, all of the ribonucleotides that are inside. So what do? We use another DNA polymerase that has an exonuclease activity along with its regular polymerase activity. And this would be in prokaryotes DNA Polymerase One. So what does DNA Polymerase One do? Well, it breaks phosphodiester bonds of the existing RNA ribonucleotides. Okay? So in this program, I can erase. So what would happen would be polymerase would come in and break these bonds and remove this RNA. Okay? Like so. Well, I kind of made a mess of that. And so now we have a place in our DNA that's not complementary base paired. So then what happens? It comes back in and adds those nucleotides. I'm going to make these in pink. Okay. Go away. Ah! It won't go away. Okay. And what does it have to do? What does a polymerase need in order to add new nucleotides? It needs a juicy 3' OH. Well, where do we see a juicy 3' OH? We see a juicy 3' OH right here from the lagging strand on the opposite side of the origin. Right? So the last nucleotide here, which was an A, right, has a 3' OH hanging off. Right there. Okay. This T over here has a 5' phosphate hanging off the end of it. Okay, so now when DNA polymerase comes in to add complementary base pairs, it has to use this 3'OH to add the phosphate of the incoming nucleotide, which would be an A, okay, to be complementary to that T. So the A's 5' phosphate, and the new A's 5' phosphate, and the existing A over here, 3'OH. Magic happens, right? You know what kind of magic that is? A condensation reaction. And we get a phosphodiester bond between these. Right? Now this guy's got a juicy 3'OH right there. So what do you think happens? The new nucleotide comes in, it's a T, right? It's phosphate, condensation reaction, right? Same thing here. And then this last T guy, I'm going to show it up here, has a 3'OH hanging off. Now remember, polymerases cannot make this final phosphodiester bond. It just can't. It has an existing phosphate and an existing 3'OH. So what enzyme do we need to do that? Anyone? Anyone? Yes, sports fans, you got the answer right. Ligase is the enzyme that makes that phosphodiester bond. Okay, so magic occurs, condensation reaction, bingo. Those guys are now linked together. Now that's a completely solid strand of DNA. No RNA in it, and no nucleotides sitting next to each other that are not bonded together. Okay, so the exact same thing is going to happen up here to this one. It's going to chew it away, right? There's going to be that existing 3'OH over here, and we're going to fill back in, right? And so this is attached here. Right at this point, again, we have an issue. What happens? Ligase hops into that bad boy and makes that last phosphodiester bond. Right, well, what about this one over here? Yeah, it's on the other side of the origin, but guess what? There's a juicy 3'OH. We hop on that bad boy. We go all the way through, and then the connection of that guy to the other strand is also mediated by ligase. Okay, so we have essentially resolved the Okazaki fragments. Right, and if you're wondering, which I didn't mention before, the Okazaki fragments are essentially a primer and the DNA that's extended from it. That would be what we'd call an Okazaki fragment. Okay, I hope this little tutorial helps, and I will see you guys soon.